The first speaker, I'm delighted. It's Ruzena Bajcsy from the University of Pennsylvania, and I will give the same introduction to everyone. One of the pioneers of our field, one of the 6 most important roboticists there are. Ruzena, it's all yours.
I'm ready to go. Thank you very much. It's my really pleasure to be here. Probably my last meeting since I am 91 and who knows what happens. But I have been with this community more than 60 years. And I remember many of you when you didn't have gray hair and no wrinkles, and you had small children and so forth. So it's a pleasure to really, we were a family, and I urge some of you younger people, think about this community as a family, because none of us had the recipe for solving all the problems. I mean, this morning when Kuniyoshi talked about the evolution, I mean, he has been at this problem for some time. As I remember, he was a first PhD student of Hiroshika Inoue I remember in the 70s. And look how much or little progress we have made. So these problems are difficult, but they really need a village. So what I will try to show you, this presentation is extremely personal. I will only talk about my PhD students in the GRASP lab. I established the GRASP lab, but there were other professors that I had the pleasure to work with. One of them, dear friend, was Richard Paul, Lou Paul. I don't know if he's still alive. I haven't heard from him. It's hard to get it. But there were other professors who really equally contributed to the intellectual wealth of the development, and I personally benefited from them. So let me just continue, because I was warned that I shouldn't talk too much. So here we go. I arrived to University of Pennsylvania as an assistant professor in January 1972 to the newly established Computer and Information Science Department. I don't know how many of you realize that there were no computer science departments. At Stanford, I think it was in the early 70s the department was established. The MIT had this combination of electrical engineering and computer science. So computer science was really in the very beginning. Professor Arvind Joshi was the chair, and I was the first appointed faculty. And as it turns out, I was also the first woman faculty in the whole engineering school, because in those days, nice, good girls didn't mess around with screwdriver, and engineers were labeled that they work with screwdrivers. So I remember actually, I have to share this with you guys. I remember there was a cocktail party, and the colleagues brought also their wives, and one of them came to me and said, "Dr. Bajcsy, what do you do with our husbands when you are not teaching?" So those were the days. Now, today, nobody would ask those questions, I'm sure. I hope anyway. I came from Stanford University with a PhD in computer science, also at the time newly established department. I spent 5 years at Stanford at the Artificial Intelligence Laboratory under supervision of John McCarthy. Now, John was really the father of AI, and I often think of him when, there is all this propaganda about AI. How would he feel? Because he was a real mathematician. He was a logician from Princeton. And for him, AI was all about representation, nothing else. I arrived to Stanford in 1997 from Slovakia, 5 million people, with conventional electrical engineering education. While I was a good student in Slovakia, I felt very inadequately prepared to the Stanford students. At that time, the AI lab had most capable students with high mathematical skills. Especially, there was a group of French students from L'École Polytechnique, and they knew so much mathematics. I was floored completely. They knew topology, algebra, numerical math, you name it. There were from L'École Polytechnique, as I mentioned, but there were also some students from Milan Polytechnique, and they also knew quite a bit of mathematics. And then there was from India, few. Raj Reddy was one of them. Australia, Richard Paul, of course, Japan and Sweden. I was completely overwhelmed. I picked up a great deal of mathematics. I worked 20 hours a day, and it was a pleasure, but it was very strenuous. John McCarthy tasked me to work on problems of computer vision, so I delved into signal processing, geometry, learn programming language, Lisp. As you may know or may not know, that John invented the programming language Lisp, which was very string-based. It wasn't numerical, because he really believed that knowledge representation has to be represented in a symbolic fashion. That's what his was. The students and the atmosphere at the AI lab was most friendly. John McCarthy had parties in his house every Friday. That didn't exist in Slovakia. In Slovakia, people had small apartments, so people didn't socialize at home. At Stanford, John had this huge house, at least to my eye, it was a big, big house, and so we were partying every Friday. I made lifetime friends, Erwin Sobel, remember Sobel, operator, but many others. But most importantly, I took with me the spirit of the AI lab and committed myself to copy it at Penn. So the first thing I realized, I needed a digital video camera, which in 1972 was not commercially available. I was lucky. I had an MS student, Aaron Snyder, who still lives in Boston. I connected with him. What he knew to build electronics, so we could buy one-dimensional charge-coupled device, which is like a shift register, one-dimensional, connected with vertical repeater, which provided us two digital digitizer. After months or so, we could start the experiment with 2D signal processing. My reason I'm sharing this with you guys is that we were committed to solve problems, and we did everything and anything to do that, even if we didn't have the right tools. We built them. So, if today you hear, oh, I cannot do this, I don't have this, I don't buy it. If you really are interested to learn and make progress, then you do anything you need to do to accomplish that. All right, so at Penn, you may know, was the first ENIAC, the digital computer build. And that, of course, was shown to me as an example what Penn can do. So we built this digitizer, and he is a digitized image of me. So you can see how coarse the digitizer was, but nevertheless, we had a digitizer, and therefore I could task students to take images and do some analysis. So the first task John asked me to use, I should back up. The outstanding problem, also at MIT and Stanford and a little bit more at Carnegie Mellon at those times. Those were the three AI labs existing, was that the world is three-dimensional. And the standard pattern recognition community was only studying two-dimensional images, classification, pattern recognition. And this was also in cell recognition, in medical imaging in Washington, but also in the other areas, two-dimensional. And John insisted, rightfully so, that the world is three-dimensional. Therefore, we have to reconstruct from two-dimensional views the three-dimensional world. And I bought that completely. As is obvious, our technology of image sensitivities didn't provide enough resolution in order to resolve the gradient of, well, John wanted me to look at the texture gradient. And I was struggling with the spatial resolution of the texture that I was able to digitize in order to really get the gradient from which I wanted to compute the depth perception. The power of 3D model, the representation that John emphasized was so much. By recognizing that, but then I worked on satellite images, and they give us a little, so here is an example of this texture which was in my thesis, and you can see it's very difficult to see closer to you. The frequency is lower, but then as you go further, there is a higher frequency. So I wanted to compute the gradient of these frequencies, but as I said, the resolution was not very good. So then, this slide, then it was the idea that if you do have the three-dimensional data, how do you compress the voxels into some representations that gives you at least some geometric ideas. And of course, the spheres was a very ideal primitive because it's moved in every direction. You have the same axis, so it was the right. So we took a hand and we fit these spheres as you can, and then you can take the centers of these spheres and connect them and make a skeleton out of your hand, and that gives you a feeling of, you know, whether you have a flat, the palm, or you have fingers, and therefore you can manipulate the fingers. So I worked with Roger Moore. Some of you may know him. He was my French postdoc, and he developed these algorithms, and we published it in 1983. You see, we were already worried about the three-dimensional representation. Then, as I started to tell you, I moved into the satellite images because the satellite images had pretty good resolution. And I had a student, an Iranian student, Mohammed Tavakoli, and we took the images from the Washington, D.C. I don't know how many you know the Washington, D.C. There is this river, and then you have all these bridges. However, if you take the three-dimensional point of view, then you know that bridges are above water. And so if you recognize where the water is, and you model the bridges with a concrete, then you can remove the bridges and show how the water is contiguous, and this is what you can see. So this was an example where the three-dimensional representation allowed you to deal with two-dimensional images in a realistically substantive fashion that before was not known. And this was really John McCarthy's influence on me. The biological visual system reaches us. There are several components that are being controlled, tune or improve the contrast, magnification, and depth perception. So this whole idea of reconstructing 3D really brought me to study more psychological vision. And I would go to psychology department at Penn and listen to some of the seminars and learn about the eye system. And indeed, that helped me to build then a copy of a mechanistic system that I will show later on. Eric Krotko was really the main person who did that. But what I'm trying to emphasize to you, am I?
About a minute.
Oh, good. Thank you. I will go fast. That allowed me to. I forgot what I wanted to say. Anyway, so let me show you the gizmo that we built. You see, I don't know if you guys realize that you have a way of moving. There is a muscle between your two eyes, and you can, for certain short distances, you can get from these muscle readings stereo. So we built such a system, and of course we used the focal model of the focal lengths, and Eric Krotko, this was his thesis. Now, hanging around the psychologist, this is very important. Excuse me, I will extend my time a little bit because this is very close to my heart. We hang around with the psychologist, and it was very clear that in robotics you just don't see, but you also want to manipulate and interact with the environment. And for that, you need a way of sensing where you are, tactile, sensory, proprioceptive perception. So I lucked out. In one of these meetings, I met Georges Giraud from Toulouse, who had a conductive sensor that measured the force and converted it to an electrical signal. And I will show you, in the middle, there is that French finger, we called it, because it was, and it looked a little bit like a penis, but excuse me. But Peter Allen was the first one who used that, showed experimentally and philosophically that you cannot exist in this real world if you want to interact with the real world and only with vision. You really need also some ways of measuring the touch and proprioception. And I think if you talk to anybody in the robotics field will tell you. So this is what we did. And we also were able to show, the reason I showed that you can detect whether you have a hole or you have a concavity and so forth. So in collaboration with the eminent psychologist Susan Lederman from Queens and Robert Klatsky, who is at CMU, I rediscovered that actually psychologists have worried about that, and that I was a new baby on the. So they showed me that actually humans use different motion to probe certain different properties. And that was an eye-opener, and I learned that from the Klatsky and Lederman. So since I have to be moving. So then we realized we really needed more hands. And Ken Goldberg, who was an undergrad at Penn, I sort of mentioned this to him, and he connected with some mechanical engineers, and this is his. He designed this hand with a palm and with 3 fingers, and did some experiments on that. Then later on, I had a student, Sanjay Agrawal, who together with Vijay Kumar worked with this kind of hand and in conjunction with the vision and completed the circle. Then we said, okay, so manipulation is fine, but what about walking? So then I had this other Indian student, Prama Sinha, who built in the legs a spring device that can measure the inclination of the surface and how to, yeah, I have to move, yeah. Sorry, guys. Well, I have a lot of other things to say, but you can probably read it. I have been very fortunate with my student. We then focused very much on how to represent three-dimensional objects, how to segment more complex objects, but I cannot resist. Oh, I had Sang Lee, who did some beautiful work on reflectance and highlights and the light effects with these kind of, yeah, but what I want to really show you, which I think doesn't get enough recognition, is this issue of functionality. People are starting to talk today about interaction. Well, interaction, different devices have different functionality, and I had a student, Luca Bogoni, who studied this functionality that, for example, how do you say that this is a scissor? How do you test that it's a scissor or a knife or a whatever? And then Jana Koszecka, who I think is in this audience, she was charged. We had a mobile system, and she was charged to design system that can move around with obstacles, and so use the formalism of discrete event systems. Okay, all right, okay, I'm sorry. All right, so let me just tell you the message I want to tell you. 3 messages.
Can I get volume at the podium mics? We have time for one question while Matt Mason sets up his talk. And Regina, I hope will be around this afternoon in the keynote session. Meet the speaker. Matt?
I have 3 messages.
I hope you're here. I wish you were here.
Even if you start from a zero ground, if you are committed, you can do a lot of good things and be innovative and be creative. And don't believe that good work is done only at MIT or Stanford or Harvard.
Let's go do it now. Get him set up.